A projectile is launched from a platform that is 10 feet high at an initial speed of 200 feet per second at an angle of 30 degrees from the horizontal. Give the parametric representation and rectangular equation for this. So first thing to know is when they say parametric, they're talking about x is a function of t and y is a different function of t. All right, so anyway, the key is to remember it has a t in it. When they talk about rectangular, they're just talking about x and y. So you got to know that, but rectangular, x, y, that's all throughout the chapter. So parametric, here's how this works. For a parametric, you can look at the x equation, and it's going to look like we've got the initial speed, and we've got this angle. So the x is going to be 200 cosine 30 degrees times t. That's your function of t. Now your y is going to be negative 16 t squared plus 200 sine 30 degrees times t plus launched from a platform that is 10 feet high, your initial height right there, 10. So a couple of things about this. When you see the 16 right there, that has to do with the force of gravity. If we were on the moon or a different planet, that'd be a different number, but as long as we're on Earth, it's going to be that number, okay? So we've got the initial speed, we've got this angle. Notice sine is talking about a y number. We already knew this. This is your initial height. But those are your two equations that represent your parametric equations. When you graph this as Desmos, you're going to graph it as an x, y. So it's going to be 200 cosine 30 degrees times t, comma, negative 16 t squared plus 200 sine 30 degrees times t plus 10, close it. All right, it's an xy, it's an ordered pair. Other than that, sometimes what you can do or what you should do is actually take the trig out of it. So 200 cosine 30 is a weird number. So remember what cosine 30 is? 0.866. Okay, that's square root of 3 over 2. Square root of 3 over 2 times 200. That's going to be 100 square root of 3. So 100 square root of 3 times t. And sine 30, we go 200 sine 30. Oh, that's nice, because remember, sine 30 is 1/2. So 200 sine 30 is 100. So we have negative 16t squared plus 100t plus 10. So it doesn't really matter if you do the green or the purple. It should be the same thing. So let's check it out, what it looks like on Desmos. If you type in the trig, you're going to have to put the 30 in parentheses. Otherwise, something unexpected and undesirable happens. Bless you. When you look at the graph, if it doesn't look like our normal parabola that we expect to see, it's probably because we're not in degrees. Make sure you're in degrees. And now that's going to look like what we need it to look like, I think. Okay, so if it's not quite enough of the parabola, that's because this t value is not big enough. So I don't really know what t needs to be. Just make it big enough so that it crosses 0 and you can see where the thing hits the ground. All right, so that's kind of it. Now, if we used this purple version, some people like the purple version better. 100 square root of 3 t on it, and negative 16t squared. Okay. Notice it's the same thing. So it doesn't really matter, but what this does, what the blue one does, is it kind of takes the trig out of the equation, and you don't really need the trig. But it should be the same thing either way you do it, all right? So we still have to do the rectangular equation. So rectangular is going to have x and y in it. So let's look at that. Easiest thing to do is look at this. This is x. And so we know that x is equal to 100 square root of 3 times t. We want to isolate t, so we're going to divide by this number, 100 square root of 3. So t equals x over 100 square root of 3. That's what t equals. We're going to take that t and we're going to plug it in to the y part, or the y equation for our parametric. So y would equal negative 16, I'm going to have to write really small, times x over 100 square root of 3 squared, that's t, right? T squared, plus 100 times x over 100 square root of 3, that's t, plus 10. All I did was I took my y equation and I plugged in that t value with my x's in it. And so I'm just going to clean up that equation. The first part with the x squared, I've got negative 16 divided by, actually I need to put this in parentheses, 100 square root of 3. And I'm going to square that. Okay, great. So be very careful on that. You have to divide by 100 square root of 3 squared. If you don't do it right, you're not going to divide by the thing squared. Okay, so 0.00053 repeating. And then on the other one, you might notice those 100s are going to cancel out. So really there you just have 1 over square root of 3. 0.5774 or so. Okay, so let's clean this up a little bit. Y equals negative 0.00053 repeating, x squared, plus, what was that number again? 0.5774, 0.5774x plus 10. That's rectangular. Rectangular has x and y. That is a rectangular, whoops, oh man. Bless you. Okay, rectangular equation. So again, we had two different things. We had a parametric representation here with your t's, and you've got rectangular with your x's and y's. Now, check out what happens if I graph that equation, that rectangular equation. Y equals negative 0.00053 repeating x squared plus 0.5774 x plus 10. It's the same thing. Okay, it's the same exact equation as what we had before. Same thing. But the huge advantage that we have is the parametric representation wasn't clickable. So even though I know I'm going to be interested in this point, and you can zoom in to see what it is. Looks like 1100, 1099.6. Okay, we can zoom in kind of far and see what it is. It's kind of difficult because we can't click on it. Even the blue one, we can't click on it. As long as there's the T's in there, we can't click on it. But as soon as I put it in rectangular form, Desmos is going to allow me to click on it. So this is going to be useful. You can just look at the rectangular, and we're going to need to know this point right here, and the maximum is right here. We're going to need to know those 2 points, and the advantage for rectangular is you're going to be able to click on that and see it. If you didn't have rectangular, that's fine, but you'd have to zoom way in until you can see what those numbers are. So we've got parametric, we've got rectangular. Now find the distance the projectile flew and its maximum height. Well, that's just what I was showing you a second ago. The distance it flew is going to be right here. Oops. Right here. 1099.7. And its maximum height. Okay, we don't want the x number because the x number is how far it traveled. So its max height is its y number, 166.3. That x number, we'd say, it had traveled 541 feet horizontally when it reached that max height. Okay, I don't really like that question. I like the question of how far did it travel and what's its maximum height. Part C says find the total time the projectile is in the air. And the trouble with that one, what makes this one kind of hard, is we can't see that in this graph. You can't see the answer to that question in the graph. It's none of these points. That this is not talking about time. But of course it's not talking about time because we're talking about x distance and y distance. If we want to talk about time, we have to talk about the letter t. Okay, so when we talk about time, you're going to need one of these two equations with a t in it. All right, and so there's two different ways to do it. Either you look at this equation with the y part. All right, so check it out. We can go y equals negative 16, and I'm not going to put an x in or a t in it. I'm going to put an x in it. Negative 16 t squared plus 100t plus 10. So plus 100x plus 10. I want an x in there so I can actually click on it. And notice it puts this parabola in there. Okay, this parabola is talking about the t variable. And we can see that max height is still 166.3, but this number right here is when it hits the ground. So we're talking about the t, and when the time hits the ground, it's about 6.3 seconds, about 6.3 seconds. And so I can see that right there. T is about 6.3 seconds. Now the other way of doing it, I can actually use the other equation, and it might be easier for you if you look at it this way. We want to find the time. So we're actually finding the time when it was at this maximum distance. So what we can do is plug in 1099 right here for x and solve for this t. So if I go, okay, what was x? X was 1099.7 about. If I'm solving for t, I'm just going to have to divide by all of this. So let's divide by, put in parentheses so we get all of it, 200 cosine 30. 6.3 seconds. Okay, so as long as you're using an equation with a t in it, it can be done. I suppose we could even do this if we took this equation and plugged it into a quadratic formula calculator or just the quadratic equation. So check it out. We've got a couple of different ways to do this. Quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. That equation was negative 16t squared plus 100t plus 10. And we get about 6.3 seconds. Okay, about 6.3 seconds. So lots of different ways of doing it. You can look at the graph. You can plug it into one of the equations. You can do quadratic formula. Lots of different ways to do that one.